many of you are working in those fields where things like fault tolerance, redundancy, perhaps exemplified by these projectors this morning or this morning still, or afternoon, early afternoon, are good examples of. And brain, if you will, to put it in a trivial way, is maybe the best illustration, at least that I know of having lots of redundancies. It's an amazing what fault tolerance is sort of nature engineered into that network, which we call the human brain, for example. We can take a lot of beating, and somehow stuff still works out okay. And to begin with, just a very quick acknowledgement about the subject matters which I'm covering. And they do bridge, if you will, neuroscience with some significant amount of engineering, which presumably is the main composition of this audience, and then on to even some clinical, i.e. medical device considerations. So that's kind of the texture of the talk. This is something that necessarily requires people across disciplines. Nothing of surprise to you guys here. In our case, it bridges several institutions, some of which are mentioned here, and individuals. So I'm simply a messenger here. Outline. So the first part, particularly people here who come with the biomedical engineering background or are students in that discipline, will be a little more tutorial, if you will. But I'm going to assume that many of you, if not most of you, have a electrical engineering or some similar sort of a professional or student makeup. So I'll be speaking mostly to you. Then after the tutorial, a little bit about sort of the current state of the affairs, which actually has a number of very good examples here on the Michigan campus, in particular in the biomedical engineering department, about how we connect some parts of the brain in a very limited way. And you'll hear and see me say how limited that is repeatedly in terms of the number of, if you will, the transistor equivalents that inhabit this piece of apparatus we call the brain. And then finally, and perhaps most importantly, where I try to reserve much of my remaining time, is sort of leaps forward, where you're trying to really enhance the current access, if you will, to larger numbers of points, or basically measurement points, almost like circuit probing points in this very strange environment, biologically, electronically, whole host of other things, which we call the brain and brain circuits, across all kinds of species, by the way. There are lots of, as you know, there are lots of animals which actually will beat us any day, any night to a certain specific task. So we're not that necessarily high up in the totem pole. But if one were to look at, to begin with, sort of the very basic tutorial ways of trying to access the brain, many of you know and perhaps have experienced in person this idea of having scalp electrodes, really remote sensing. Not very precise, but very useful for clinical purposes. If you need to understand brain's own language at the level of certain number of circuit operations that would go, for example, for me right now, planning to move, before I do that, my right hand and an arm to some location. That's very hard to do at this level of signal extraction and decoding and so on and so forth. Signals are simply too distributed, if you will, or unclear. You can go below the skull, so this is immediately medically invasive and would not be taken and done any light fashion, but for very good clinical reasons, say of epilepsy monitoring and so on. Things that have these little dark dots here would be electrodes sitting right on the brain surface, not inside, but on top of the brain surface. That gets you a little closer to the action, which is a few millimeters below the surface in terms of the all-important cortical landscape of the human and mammalian brain in general. And then finally, you may want to go literally inside, and that's a bed of needles, perhaps not visible. I'll review that in a moment in a different context, which is called the Utah array in the language of things. There's also a Michigan array, so I wanted to make this very clear that there are two states that have really distinguished themselves in having created these so-called intracortical microelectrodes, which are silicon-based micro, I should say, not nano, probes where each one of these needles will be a site of measuring something that might actually be responding to a single neuronal cell or some tens of micrometers in spatial extension. So these latter are the ones where you do have to go inside. The payoff, of course, from a fundamental and clinical point of view, you're so much closer to the action that you can actually read out certain things that you would not be able to do, at least today, remotely. I'm going to skip this, but just to say that in terms of a single microelectrode, let's say a little needle which might have micrometer dimensions in terms of at least the tip where the sensor part that draws out signals that would correspond to some voltages and currents that the neuronal circuits are inherently creating. That's basically the probing mechanism. That these are then extracted through, in case of these below the skull in the brain implants, they are extracted through essentially parallel point connectors, not unlike the ones that we were struggling with a little while ago. I mean, that's basically the methodology. And then sometimes things work and sometimes they don't. But nevertheless, the illustration, which may be familiar to some of you, certainly the ones who are from biomedical engineering from the neural prosthesis lab that Cindy Chestek here runs with colleagues, is this video. Let's see if it plays in this PC to Mac translation, by the way, which is a moment of some excitement always to a speaker. So this is a person who was paralyzed by a stroke from head down. And so a quadriplegic individual. And what the video narrated is actually this bed of needles surgically implanted in her brain, a percutaneous, meaning a connection path, electrical connection path from each one of these approximately 100 little beds of needles or individual needles to a signal collection box here, again a parallel plate plugged literally on the head and the skull, and then a cable that translates those multi-channel signals to nearby receivers, electronic receivers, and importantly, computers that will do the decoding. So the electrical signals, as many of you know, that brain creates are mainly in forms of almost like a digital things, little spikes, which are called action potentials, milliseconds in duration, and they may run if a particular neuron gets really excited up to their physiological limits of a few tenths of hertz, something like that, repetition rate. And that repetition rate is basically the signaling piece of the activity that neuron is performing in concert with its sisters and brothers that may span millions of nearby and more remote neurons, all wired in multiple ways that any permutation that you can imagine, 1,000 objects could be reconnected or interconnected would be happening. And the important difference, just to pause here for a second, in that anybody who comes from a traditional physical science and engineering background, and by and large is used to, for example, laptops and integrated circuits, they are extremely predeterministic. There's nothing really uncertain about it. In fact, we drive ourselves crazy in trying to make them as perfect. No bit error rates are allowed, whether it's on board here, telecommunication, and so on. That's all the bad stuff. Whereas the brain circuits, by their very design, are very stochastic. So this repetition rate, which I could have shown you in a different slide, but I'm going to concatenate this talk, would be a kind of a series of like machine gun firings, but kind of an erratic one at that. And that doesn't mean that there is not a message. There is a message, but it's encoded in this kind of stochastical language, which at the end of the day, if you will, in my view anyway, from rather fundamental points of view, gives robustness to this kind of communication, perhaps a little counterintuitively. But when you have lots of that stuff going on in parallel from hundreds or thousands of places that kind of create their mutually coupled excitations, that's not a very inefficient way of doing it. It's actually a very efficient way of doing it. So our brains, as many of you may know, probably burn up to about 20 or 30 watts. Steve Forrest, somebody like that, will go to 100 in no time at all. But kidding aside, and we do things, right, which a mere laptop could not even aspire to. I mean, we don't multiply 8-digit numbers, in a millisecond, that's for sure, a microsecond. But we do so many other things. So it is an impressive piece of apparatus. So this woman, was able to basically, after the decoding of these neural signals, and there's a real science, mathematics, science, to some extent art, in decoding or deciphering neural signals which you obtain for large numbers of points, which don't really make any sense to a naked eye or even to a educated listener or observer. But then you do resort to algorithmic techniques which are beyond this talk. Again, very sophisticated applied mathematics field, from which then the intention of this person that you just saw to move, imagine the movement of an arm or a hand, which she cannot do because she's paralyzed from neck down. That intention is decoded from the electrical signals, and then it was guiding the robotic arm and a hand that gave her the sip of drink for the first time on her own volition in about 10 years after the event. So this particular construct, which I refer to as the Utah array, as well as the analogous Michigan array, first of all, there are all sorts of regulations, biocompatibility, as well as safety and so on. So this is really an FDA approved before you go to a human. But the very useful initial tests were done in monkeys. And the reason why I say that is that the issue of longevity, among others, was established to be several years if you know how to do things right. If you, it's not actually coated. These are platinized tips. I mean, that's really the business end of these electrodes is platinum. And that turns out to be, platinum is relatively inert, and it's not bioreactive, at least to any first order, as far as I know. So that's the good news. The bad news is that there are certain other insulation aspects in this construct, which fare less well in the body environment, which is mainly seawater-like, without bringing any biochemical or immunological reactions. So the jury is kind of out. If you're asking me, can I put one into, or somebody put into you, and you'd be comfortable for 10 years or 20 years, I'm not sure. So that's state-of-the-art kind of thing. But for assistive cases like the ones that I'm showing, where you have very serious and severe quality of life issues, including in our clinical trials led by my colleague, we have ALS patients and so on and so forth, all kinds of other very serious health questions and issues. What's happening here is that you can see a keyboard. It's a little specialized keyboard. It's not your regular layout. But this is from our collaborators at Stanford, using the very same techniques with emphasis on this decoding algorithmic approaches that are increasingly beginning to use machine learning. And so what the patient who is, as you can read from the legend in the bottom here, is unable to move actually physically at all, and obviously in a very bad situation with ALS and so on, not a curable disease, but she's able to imagine the movement of an arm up and down, left and right, and then something akin to a click, which we would use in a computer mouse. And so through this process, I have maybe concatenated a little bit, but in this process of evoking thoughts, reading out the thoughts for making a movement, which she still can do because the brain is intact in this particular case, for instance. She can translate her movement intentions and actually visually herself watch the computer cursor, which is controlled by her thoughts, on a screen to type up messages. And as a consequence, there's a communication interface to the rest of the world. I mean, you now have yourself, your brain in a way, albeit with some assistance, is connected to the internet, if you wish. It's another illustration of this technique where you have maybe 100 or 200 of these little probe points sampling, literally a test bed or a volume of microcircuitry in the brain that might have 1 million or 10 million neurons. You're undersampling like there's no tomorrow. 1 in every 10 to the third, 10 to the fourth neuronal site is being picked up like a little seismic detector, and try to predict the earthquake kind of thing. That's sort of the metaphor, perhaps, that in this particular instance, the very same undersampling toolkit in a non-human primate, i.e. a monkey, in our labs was used to not record intention to move an arm or a hand, where monkeys and humans are very similar. They're actually much better than us in terms of the speed and so on and so forth. But in the sensory side, so we have places here called the auditory cortex, which again the biomedical engineers would know, or clinicians if there are any in the audience. And we implanted these into the auditory cortex of a monkey, and then had the monkey or monkeys listen to English words, a whole bunch of English words. I mean, the monkey doesn't understand that stuff, but that understanding happens in a different part of the brain. But the auditory cortex is a place where one is interested in trying to figure out how the brain interprets all the stuff that goes through the ear and what kind of signal texture is being converted, converted to. So I was going to show you, because the example here involves heavy-duty machine learning techniques in this decoding business, which is kind of where the field is going, in part at this stage of the game with this limited set of probes. And you would have been, at least I was very impressed by my guys who were able to make sense after decoding these electronic signals from the auditory cortex, words like cricket and good and any number of sort of contrasting spectrotemporal vocalizations, reconstruction into auditory sounds that you would listen. You would think it's an English speaker actually saying these things to you. So the examples I showed you, they always have this implementation from an engineering point of view. I'm looking for a parallel plate. Yeah, here. I mean, here. No, it's not exactly. But you can imagine a 100-pin connector, and you screw it on, and you should generally have a pretty good electrical connectivity and so on. But it's not going to be particularly mobile. I mean, if I'm hooked up to this kind of ensemble of these projectors, I am very unlikely to move around very, very far, very fast. And if I'm disabled up to a point where many of our so-called clinical trial participants, and I'm only the engineering appendix, by the way, to this team, they are wheelchair bound, but they can move around. And so the question is, if you would like to have your little laptop as a visual screen and you'd like to send an email or text or something like that, communicate with your children, whatnot, you might want to do it in your living room, in your bathroom, what a number of things, but at least in some sense of mobile setting. So it brings immediately the question of wireless and somehow manifesting itself in a way that makes sense in this rather complicated sort of application environment. So first of all, there's a question what you can do within the body beyond those purely passive sensor arrays. So the ones that I have spoken up to this point are basically these little beds of needles, which are surgically implanted by specialists into the brain cortex, whether it's the motor area, which is where we plan things moving and so on and so forth, auditory cortex, where we figure out what the words and sentences mean to first order, or visual cortex, which is back here, where we map visual scenes like this very attractive scene here that I'm seeing, and so on. But the devices are just passive. They are just little beds of needles, and all the electronic activity happens outside after the end of the cable. So if you go wireless, the question is where are you going to put your radio, basically, because you are talking about wireless transmission, or what becomes very quickly, not huge data rates, but if you kind of get this aggregate of 100, 200 channels, as we call them, with this present implant electrode arrays, it will run up to 100 megabits per second, 200 megabits per second, something like this. So not 5G, not like that. But nevertheless, it's a very application-specific environment. So you could put some of the stuff inside the head, and there's a big difference whether it's below the skull or above the skull. I mean, that's a kind of a surgically important division. Outside the body, very standard stuff. I mean, we know all this from telecom, and some of you may be from the telecom part of the electrical engineering. So this would be kind of ho-hum for you. except that it has to be, again, tailored and customized. So nothing is really off the shelf here. And there's some legend here that talks about some of the sort of parameters and requirements and so on, including the all-important power. I mean, power is sort of like everything here in terms of how long certain batteries or energy storage or energy transfer and stuff like that, and safety. So I probably will skip this because, but only because of time, but only because of the notion that if you already have this plug on the head, you could say, well, I mean, that's a fairly, if you're an engineer and silly engineer like we were and still are, why don't we just, screw a transmitter, get a little wireless dongle. So this would be the kind of the physical plug sitting on the skull. So I'm going to just put a little radio there. I mean, I do have to work a little bit on telecom stuff and so on, and not to bother you with the details, but these are kind of known things, and we worked it out a few years ago. Actually, Cindy with folks at Stanford was also doing this a number of years ago. I want to make sure that anybody who watches videos that has animals like monkeys is sure to know that we do all this work under very strict regulations. These are FDA mandated regulations, and these are monkeys whose welfare is hugely important to us, even if they will have surgically implanted electrodes. You're not going to be able to see much here except that he's going to be walking on a treadmill. It's not totally natural movement, but nevertheless, he's got actually a pair of transmitters from two different parts of the motor cortex. So as you and I would be planning a gait to move, there are certain processes in the brain that under visual guidance will tell us, when to put the right foot and the left foot first and the right foot forward and so on and so forth. So it's not a scientifically very deep demonstration. I'll just play a short clip of it. But all the stuff on the right-hand side, so these individual little specks correspond to the following. Horizontal axis is time, more or less on the scale of what you're watching here. Vertical axis is each one of these horizontal rows is a particular electrode needle. And these little blips are those little action potentials. So their repetition rate is sort of modulated as something happens. And this runs across all the number of electrodes. And if you were to visualize, try to figure out what did that actually mean, there would be no way to figure out, what am I watching, this temporal pattern, if you will, right? I mean, it doesn't really make too much sense. And so that's where the decoding, the decrypting comes in a very important way, okay? So this particular device, and again, because of the safety and any number of other considerations, before you get even close to a human with these sorts of radio frequency devices that transmit neural signals from the brain, it's more than just going to somebody and saying, well, after all, I had this, this person with a plug and a cable, and now I have this little radio, so I'll just do it. No, I mean, it does take FDA approval for a very good reason. And that's a fairly recent, I don't have a video on this here on my laptop, but it's from the collaboration between Brown and Stanford. And what you're seeing here, it doesn't look necessarily very pretty, but it's a very powerful enabler for this person who is actually an ALS. So this is a Lou Gehrig's disease for those who may not remember. So we're talking about very serious and neurally degenerative condition for which there is no recovery. But he's otherwise in pretty good health. He's able to somewhat verbalize, but he's totally immobile by this time. And what he's doing is communicating actually through, he's typing on the screen, okay? And here are actually, in this case, two wireless devices, these things that we built at Brown, designed and built and so on and so forth. And so he's in a wheelchair and he's wheeling around. Now this photo was taken by clinicians for clinicians actually, so I would have done it a little differently, but the distance, the transmitter distance here is a few meters. So here is one of those radios blasting maybe neural signals at 200 megabits per second, maybe a little less, give and take. There's many of you who are in the RF business will recognize an antenna. I mean, So it isn't really super duper RF gear, except some custom stuff for sure here, and so on. And then he's, he's smiling actually, and that's not a fake. I mean, it's true because he's reading, I think, message coming back from his daughter or some such thing, and messaging back. You know, again, by this conversion from his intention to move the equivalent of a mouse, watching the screen, seeing the mouse move, but doing this all through this mechanism by which the brain signals of intention are converted into electronic signals that actually move the physical mouse or its equivalent on the screen as a cursor. But it begs the question that if I have this amount of sort of, let's say in context of movement, this amount of degree of freedom, as opposed to any number of other things, just in terms of motor action, if you will, or movement action, it begs the question, how much can I do with these 100 little needles? Is that sufficient amount of information if we have a complexity of a task at issue? Neuroscience theorists have actually speculated and estimated these sorts of things. And unsurprisingly, it does become pretty clear fairly soon that for complex tasks, whether they are motor-driven or for that matter sensory, complex visual seen as dynamically varying and so on and so forth, that those kinds of things do require multiple sites of access, one way or the other, into the brain circuits. I'm going to skip this piece because we've also gone actually below the skull and we've implanted the entire radio now right next there and so on and so forth. That's an FDA under FDA review. So that's really the kind of the lead for the short and last segment of this talk, and that is the following. So what I say yesterday, I mean these kinds of needles and various kinds of, on the scale of 100 channels, as we say, number of nodes or electrical points of probing, all within a few cubic millimeter space, if you will. That been very difficult to scale them, in any obvious way too much beyond 100, or at least in terms of clinical translation. This is sort of where we are. Now, in parallel, in the last 4 or 5 years, there have been all these sorts of multipliers of the number of electrode sites, including, by the way, here, and in no particular order, number of academics. Elon Musk, whose name may be unknown to everybody here, but from SpaceX to whatever neural kind of like thing, as a company, and this one is not that company. It's another combination of Genelia Farms, very strong biomedical base places, many of you know, and IMEC in Belgium, which is a microfab, and so on, where you actually decorate these kind of Michigan-style blades with large number of electrodes. Because it's silicon, so anybody who works with silicon will say, I'm going to build circuits on and in and out and whatever in the proximity of silicon until my heart runs out of juice. And so in so doing, the little electron micrograph here of this individual nearby for 50 micrometer bar, in case you don't see it, give you kind of the sense of getting up to perhaps 1,000 channels. If you begin to multiply the data rates and everything else that you have to worry about to get those signals out in some form or fashion, and with minimum amount of latency, by the way. I mean, our reaction time, just to put a point on this kind of neural prosthesis applications where you need to convert, that is decode, acquire, convert by decoding, and then implement some robotic or some equivalent tool. 100 milliseconds is kind of a long time. I mean, you and I, if I have 100 millisecond latency in terms of like moving my mouse here and before something happens on the screen, I notice that, and so will you, okay? So there is this idea then of actually building in certain amount of circuitry to multiplex when you have large number of channels, which is kind of generic in so many areas of electrical engineering anyway. that is perhaps only getting you so far in terms of where the next few years in translating some of these things through animal studies to possibly humans. And what I want to just touch on is something kind of a little wilder and beyond that. And that's saying, well, if I have microcircuits and if I collapse them as neural sensors to scales which are on this 100 micrometer or so, and manage to get them into the brain literally by the hundreds, if not thousands and beyond, and have them independent reporters of neural activity wirelessly. Now that's kind of the dream here. We've been pursuing it at Brown with colleagues, particularly at UCSD and a little bit at Qualcomm, now for about 4 or 5 years. First initially from the concept, the hard work in the last 2 or 3 years. And so that's a total cartoon. This is like a science fiction cartoon, where you'd have these things that we call neurograins. There are other groups in other places that have different names for these little, I'll call them cell phones for lack of a better word, which would be sort of the equivalent of, this little cell phone somewhere in the nook and cranny of a brain circuit, and it's listening and it's going to report that to the big mama out there, if you will, kind of rough translation of this kind of a hub here, communication hub. So in that concept sense, this intersects many strands of electrical engineering. Small circuits, CMOS custom designs, telecommunication, networking, wireless powering, because you have to power these objects. They are not going to sustain unless you're very clever at some point in turning electrochemistry of the body into local power supplies, which are also projects elsewhere. Not clear how it's going to work out. That you would have these sorts of challenges here. Stuff a lot of electronics into basically a couple of 100 micron worth of silicon chiplet area. Power will, you have people here, very good people. I actually met 1 or 2 earlier today about wireless power delivery and how do you really be very clever about that through what is basically in the microwave region, particularly heavily absorbing medium. The water comes in any biological tissue as really the opacity contributor, anywhere from 1 gigahertz roughly, I don't know, to 1,000 nanometers, to 1 micron wavelength. I mean, there isn't an awful lot of transparency in liquid water in between the RF in that sense and the near infrared, right? I mean, we know that already for 5G. I mean, we're having some challenges in vapor, which is a little bit of fog around 28 gigahertz or whatnot. And then the telecom is networking here, and there are very good principles, of course, out there in the radio frequency, and particularly in the cell phone telecommunications industry. But the distances now in this case and many other things that don't scale actually that way need to be thought through. And then, by no means the least, you put an active electronic chiplet somewhere in somebody's head or anywhere else in the body, you better have it sealed. You better have it hermetically sealed for a long time. Now, I'll just skip through some of these things, okay? And that's going to be basically it. So multiple challenges. Keep that in mind, please. So this actually elaborates the concept a little bit in sort of electrical engineering block terms. You would have on the sort of the hub side, which you could imagine being some sort of a total antenna structure. It would still need to be, for all practical reasons, many reasons, fairly near the top of the scalp here. And then there would be a near field inductively coupled link. It's very hard to beat Faraday, by the way. Boy, I mean, it's just very hard in these sorts of energy transfer short distance applications, as so many of you know. And then get back into a single chiplet, which, I mean, the current size that we have, these are actually functional chiplets. They're not quite as small as we'd like to, but they're good enough to have shown a prototype proof of concept. So you need to have an energy harvesting block. You need to have some sort of a bidirectional communication, right? Commands going down, fanning out to these population ensembles of neurograins, as we call them indeed. And then some backscattering, which is really the mechanism of getting information back, having certainly addresses on board, not unlike an RFID tag and all that sort of thing. And then if you, in addition to the recording, pulling out neural signals, want to do the inverse, which I have not time enough at all to address today, fascinating topic. How do you actually write potential information? How do you inform brain of certain things? By sending in electrical signals at multiple points that might mimic, like listening to a sound or some such experience. This is the kind of the current example, and I'm showing you through 3 different lenses. You're looking at a top view of a microphotograph of a silicon chiplet that has various little footprints for various kind of pieces. So there's a rectifier piece. Oh, let me start actually. So what this band here, it's simply a coil. It's a planar coil, 3 turns, Y3, why not 4, why never mind. Why not ferrites? Well, this is 1 gigahertz that we're working at, so there are no really good ferrites, although we're working on that too. But there's a rectifier block, there's an oscillator, so these things have independent clocks. They have free running clocks. It's very hard to implement any sort of a systematic clock. Process variations alone and powering factors and so on. AFE, some analog amplifiers and so on. These would be a contact pad locations where you actually bring in the electrode, the pair of electrodes that sends the neural signals and so on. Somewhat similar to the so-called stimulation, that is the writing part of the neurograins. And then I'm sort of isolating these functions here. The networking part, that is the telecom part, needs actually a certain amount of finite state machine space. I mean, there are all kinds of digital tasks. It's all digital circuitry, by the way, of course, and so on and so forth. So we chose a 65 nanometer CMOS RF LF process, and that means right away something to some of you, okay? For multiple reasons, and that's what we'll be working on. Now, there are details here which, if there was a little more time, I would expound on. But suffice it to say that again, this is a situation where you have to go to work from ground level up by knowing the overall questions and goals that you want to achieve and the constraints that are imposed on you by the fact that you'll ultimately be in a bioenvironment. The addresses, okay, so just as an example, so let me stay with this in the next slide for a minute or so. What you're seeing here, and this is nothing really particularly new, but to write an individual address, so 16-bit, for example, is sort of more or less the going. This is a lower prototype. 16-bit address will get you something on the order of 1,024 grains, which all have individual addresses. And we implement an address on a tiny little footprint piece of that 500 by 500 micron chiplet by laser drilling, breaks into metallic contacts. That is not new in itself, but it is part of the post process, which has multiple other elements. So this is not something that you would just turn over overnight and so on. So we drill laser edge bridges and so on and so forth, and create a particular combination of ones and zeros thereof as an address. There's also there are probably people in the audience who are experts in this idea of physically unclonable functions. By the time you get to these kinds of gate lengths and process nodes in silicon CMOS, you'll have process variations actually at the level of things like VDD and some other sort of sub-derivatives of the voltage. And they'll give you actually randomized fluctuations which we turn into an address. Okay. So last piece here before we stop today, and that is the actually next to the last piece, if you can bear with me a little bit, is this call and response wireless protocol. So To put this in a pedestrian way, which is the best I can do because I'm not the expert in this, we have Vincent Leung at UCSD and one of my people at Brown who are telecom savvy, digital telecom. So this would be some ensemble of these neurograins. They all have their individual address. They all have their freely running clocks, typically at about 30 megahertz. That kind of gives you the enough sampling rates for all kinds of purposes on board. And you need to you send in this RF command. It's a single channel command from what we call the skin patch, which is the antenna on top of in this case, the animal's a rodent skull. And the call and response, as the name implies, and again, it's a phrase that's known to many of you, simply says that you're going to have to establish some kind of a handshake. And you have to establish a synchronous handshake. So if the clocks are freely running at will, it'll take a particular protocol to do that right. And we spent probably better part of a year in figuring out how to do that. So these are the sub sort of titles or sub talks, if you will, to the process. And that particular slide just simply talks a little more about the fact that you have this amplitude shifted key and pulse modulated kind of a digital manipulation, kind of to figure out in this first, few sub microseconds to figure out this handshake. Like, hey, I'm talking to neurogain number 111, not 113, right? So those kinds of things are perhaps a little bit more particular to our kind of space and application. There's a little more of the same, and again, if this was a specialist talk, I would, or had a little more time, I'd expound on that a little bit. But basically, there are digital tricks, some of which have been ported over from telecom as it is, and some of them have been just innovated ab initio by the team in question here. Yeah, this is the last piece, which those of you who come from material science background, this may be the only point of literal intersection. And that is the packaging. So again, these are top view micrographs of these neurograins whose thickness, by the time you thin the silicon, you're down to 20, 30 microns at the dye level. And so I was looking for ways to package these things. Now these are little chiplets, obviously they have sharp corners, there are all kinds of things in terms of geometrical form factor that makes it not so obvious whether you should, for example, try to use polymers or whatever is your material strategy in ensuring at least proof of concept of some longevity as hermetically sealed chiplets in a saline, seawater, in other words, body fluid mimicking environment. So in this example, we turn to atomic layer epitaxy and the interaction with a particular company in my native Finland called Picosun, who made their name in a sense providing gate oxides for FETs for semiconductor manufacturers. And so we ended up doing a 10-layer stack, still only 100 nanometers. That's the beauty of it. So it's a very thin, durable coating, and it turns out to be quite conformal. Here is a cross-sectional view of a particular, or piece of a cross-sectional view of a particular chiplet. So that would be the edge. That would be the normal edge, the cleaved edge or the diced edge. And the white band here is the 10-layer coating. So that's the structural evidence that it does do the trick. And then what you do, and this is kind of generic in this business of biomedical implants in general, of active electronic devices in any case, you go into hot saline or some buffered solution thereof that mimics the cerebrospinal fluid, for example. And you heat this up to 80, 90 degrees centigrade. It's a little bit empirical, but that from Arrhenius laws and things like these, you could argue that if you make a measurement like that, you can extrapolate to what it would be at body temperature, 37 Celsius in our case. And so these are not spectacularly long-lived chiplets in terms of the hermiticity that was being monitored by this RF backscattering. So they were being powered all the time in this saline bath and backscattered signals. So we would kind of interrogate their health, if you will, against any kind of breakage or compromise of the hermetic seal. And we actually stopped at a couple of hundred days. The student and the postdoc, postdoc had to go back home, and the student didn't want to spend a thesis, like lifetime watching, little chiplets dissolving maybe in saline. But kidding aside, so this actually does, by using the methodology, which you could argue is not really precise enough and so on and so forth, but nevertheless suggests that these kinds of ultra-thin coatings, and the thinness is important because you already have a small object. You don't want to add a big blob of something that compromises the viability of implantation into the brain, which always will displace that equivalent amount of neural tissue, healthy neural tissue. So that's kind of the ultimate calculus, which medical people know, at least empirically, as to how much damage can you incur. Damage in the sense of shoving something into the brain and therefore displacing that piece of active circuitry and its associated life-supporting structures, including microvasculature and so on. So we are at the moment, we're in rats, so that's maybe enough to say. And both recording and stimulation work. These are not long-lived rats, these are still short-term experiments, so you would have, rats, by the way, just to be clear, those of you who have not worked with rodents, which I suspect is like most, these Labrador rats, they're really cute, they're really nice, they're extremely friendly. So just understand that, please. So he's got, I think, 64 what we call neurograins, and his head is small, so you can't really stuff too many things in that. But he's moving around, and we're recording signals and so on and so forth. So animal is a test bed in a good way right now, but it's important to establish that for at multiple levels of this multiple engineering set of challenges, all the way from circuits to communication to hermiticity to this and that, okay? Not to mention the functionality of actually being able to read and write properly. So I'll just jump into conclusion. First of all, even if I increase this number of little probe sites, now it depends on the cortical area or volume in question. Motor patch, the one that is mostly responsible for this kind of stuff, is probably about a centimeter squared, to a couple of centimeters squared here. And the sensory part that reports the touch, is right next to it, actually, about the same area, and so on. So there's some functional division. But even if I went to tens of thousands of these little probes, the number of neurons underlying that is still huge. But nevertheless, the combination of knowing how to read out those signals electrically and then all importantly, how to decode them. And again, whether it's weather forecasting, whether it's seismic activity, where it's having a bunch of little buoys in the ocean, and watching, tsunami. That stuff is where artificial intelligence comes in a really pleasing way. You're looking at patterns, some undersampled pattern, and you're creating pictures out of that in a naive way of expressing it, but it is very powerful. But nevertheless, there is this wireless implantability, getting more nodes for sure. We could not, if one of those patients right now was imagining moving, playing a piano, this couldn't do it, okay? And so there's no question that is, for at least from an engineering challenge point of view, you want to go there because you know that there could be a payoff, and there's lots of engineering challenges and fun and, well, pain too, but combination and so on. And as always, animals in vivo, that is live animals, sooner or later you have to be there in this kind of business. If you're not going to be ready for whatever comes thereafter. So with that said, thanks very much indeed, and thanks for your patience. Thank you.